Okay, so everything we've done in the previous several videos is to get to this equation that tells us how we can calculate the change in Gibbs energy for a reaction that's happening as a function of how far that reaction has happened. And so it's going to depend on the standard Gibbs free energy. That's sort of our reference point, is the way I think of it. Just like it's used in the chemical potential equation, that's sort of our reference point. And then the reaction quotient, RT natural log Q, we have this extra term. And so, you see this behaves, this looks very similar to the chemical potential, and there's no coincidence about that because this came from the chemical potential, right? We have something like a mu naught plus RT natural log of P over P naught, right? This comes from this equation. But now we're just taking into account that we have all the stoichiometric coefficients, and we have the partial pressures of each individual component, and we're looking at differences in those and things like that. Okay, so this tells us if we can find Q, we can find then what's delta G for the reaction. That will tell us which way the reaction is going to go. If delta G is positive, the reaction will go in reverse. If delta G is negative, then it'll be spontaneous and go in the forward reaction. Now, what about equilibrium? That's generally what we're thinking about, is when do reactions reach equilibrium? And that will be, by definition, when the change in Gibbs energy goes to zero. When that extended reaction reaches a certain point, the Gibbs energy no longer is decreasing and reaches a steady state. And that is, that's when we reach a minimum in the value of G as a function of how far a reaction has gone. All right, so this is our equilibrium state. So this allows us to then plug this into this equation. We say that equals 0 will be equal to delta G naught plus RT log, and we call this now K. So this is now the equilibrium constant because we are at equilibrium. Q doesn't have to be at equilibrium. The reaction quotient is not necessarily, it's just whatever pressures you have in your system, you plug those into Q, you get a value of Q. It's not a constant, not at equilibrium, not a constant. Q is going to change as your reaction proceeds. The equilibrium constant, on the other hand, is a constant value because it only happens when the system is at equilibrium. We are going to define this specifically as Kp because this is the pressure version of the equilibrium constant for gases. We can also define it in terms of concentrations, as we'll see in just a little bit. Okay, and so we can say, all right, that means that delta G naught, the standard Gibbs energy, is equal to minus RT ln Kp. And this is a really fundamental relationship relating the standard Gibbs free energy to the equilibrium constant for a reaction. And we can say that Kp is equal to, again, the same, not A, Z goes on the top. I think we did Y first. Py to the new, not Z, new Y, Pz to the new Z, Pa to the new A, Pb to the new B. Now, one thing I've done, and what's often done when we write out equilibrium constants, is we've left off the P naughts, right? And that's because P naught is equal to 1 bar, and so as long as we express our partial pressures in bar, they all cancel out, and the equilibrium constant has no units. So we have to assume that all these PA values are in units of bar. Otherwise, the equilibrium constant won't work, right? Because that's the way we've defined our standard state. So that's something to remember. And the other thing is that we can rearrange this equation, right? If we divide by negative RT, we get delta G naught over RT minus RT is equal to natural log of Kp. Or we can say that Kp is equal to e to the minus delta G naught over RT. Right, so these are just two different ways of writing the same expression that relates the standard Gibbs energy change for a reaction to the equilibrium constant for a reaction. So this gives us a very practical way to find equilibrium constants. If we can calculate the standard Gibbs energy, we can calculate the equilibrium constant for a reaction, which can tell us a lot about how that reaction will proceed. And again, all of this came from chemical potentials. So there is a reason we've been talking about chemical potentials this whole time, because it really does tell us about the thermodynamics of what's happening in our system.